Hi, and welcome back to another LeetCode problem. Today we're looking at LeetCode 3211, generate binary strings without adjacent zeros. I have not attempted this problem myself, so this is the first time that I'm actually looking at it. And we're going to do our usual, where we approach it in a systematic way, in the same way that we would approach a problem when we're asked one in an interview. So the first step is to read the problem description. Then we need to figure out what the constraints are. Typically would ask the interviewer. On LeetCode, we are given the constraints, and then we will look at a couple of examples to understand how we might be able to solve the problem. And then, for bonus points, we are going to give an implementation idea and a runtime and a space complexity analysis before writing a single line of code. Most people do this after the fact, so it's a little bit of a flex when you can give that right away before you start writing your code. Yeah, and then we'll walk through writing a code, explain it, and then finally we will go through the code with a mental debugger. We'll take one of these examples and run it through our code to make sure that we don't have any bugs. And then, after we are confident that we got the solution right, we will try to run our code for the very first time. And that is to avoid these nasty run and error loops where you're basically just poking around, trying to find what the next error is, and then fixing that error and repeating, which is not very good when you do that in an interview. Sometimes you can avoid it, but we want to try our best to do so. So anyways, let's get started. So we're given a positive integer n. Binary string x is valid if all substrings of x of length 2 contain at least one 1. Return all valid strings with length n in any order. Let me read that again. A binary string x is valid if all substrings of x of length 2 contain at least one 1. Okay, cool. So that means we cannot have substrings that have 2 consecutive zeros, because that means there exists a substring of length 2 that doesn't have a 1. All right, constraints. So we're guaranteed to have at least one digit in our string. And we have an upper limit for the number of digits that are in the string. For our runtime and space complexity analysis, we're going to ignore this upper bound. Otherwise, everything will be O of 1 time and O of 1 space automatically. So, but that's not interesting to us. We want to know what the asymptotic space and time complexities are as the length approaches infinity. Let's see. Example number 1. So the input is n is 3. So, so we're not giving the string x. We're giving the length of the string. And that means we should have a look at all of the strings of length 3. And return them if they are valid, according to our definition of above. So, and here we can see that all strings that contain a 1 that contain no 2 consecutive 1s are valid substrings, right? So the valid of strings, yes. Example 2, a string of length 1. The output is 0 and 1. Why? The valid strings of length 1 are 0 and 1, but I thought a binary string is valid if all substrings of length 2 are. So if there are no substrings of length 2, it's automatically a valid string. Okay, interesting. So that's kind of an edge case that we need to take care of, because we might receive just one, a length of 1, which is this case. All right. Okay, so let's see. So here we're only giving the output, but we're not giving the construction of all the other strings of length 3. So I think it would be useful to go through constructing these substrings to see if we see an algorithmic pattern that we can translate to code later. And let's do that. So we are giving n equals 3. N is equal to 3. Now the first string we could do is all zeros, but that wouldn't make sense. We know that if we have a 0, the next character cannot be 0. So any 0 has to be followed by a 1. But we do have the choice if in the beginning, so let's say at index 0, if we put a 1, if a 0 or a 1, so I equals. That is the choice that we have in the beginning. Now, if we have a 1, we can, it's the same case as the base case. So we can append a 0 or a 1, but if it's a 1, we can only append a 1. Right? So, and what is interesting is we can then continue this. So since we appended here 1, the next we can append a 0 or a 1. Now, depending on what we just appended, we might have to append a 1 or a 0 or a 1. So this would give us all the substrings. So 0, 0, 0 or 0, 0, 1. That is from this, how do you say, development of the string. And this one would give us 0, 0, well, 0, no, 1, 0, 1 or 1, 1, 0 or 1, 1, 1. So those are the choices that we have. Wait, this one is not correct. 0, 1, 1, 0, like so. And the other one is like so. And what we can see now is that all the different choices that we came up with are distinct, but we didn't generate all of them. So I guess, yeah, maybe we should do that. Let's do that for length 3 so that we get all of them. So the first one starts with a 0. I'm just going to do it like so without the comments. 0, if we pick 0, we know we have to pick 1. At the same time, if we start with 1, we can attach a 0, or we can attach a 1. So 2 choices down here, 1 here. Now, if we want to continue this, we either put a 0, which we can, or we can append a 1. Let me just write it like this, yes, or a 1. Next, here we have the choice to append, well, we only can append a 1, but in the bottom case, we can append a 0 or a 1. And in this case, it's the same. We have to append a 1. Here, we can append a 0 or a 1. So, right. So this means we will have the strings. Wait, I made a typing error. We have to append 1 if it's 1. If it's 0, we have to append 1, but then we can append 1 or 0. Okay, cool. Sorry about the confusion. So that's what we do. And then the final strings that we have are 0, 0, 1 and 0, 1, 1 and 0, 1, 0. And down here we have 1, 0, 1 and we have 1, 1, 0 and we have 1, 1, 1. Okay, and now if we look at this, we see that all of them are distinct and they are exactly our solution. So I guess if we use that logic, we could implement a recursive solution that builds all of these strings quite easily. So that's what I will do. And we have a branching factor of 2, right? So if n is 3, we will have 2 to the 3 different ways of we have 2 to the n different ways of possible substrings of length 3. But at every second branching, we have a branching factor of 1. However, 2 to the power of n is still an upper bound. So in terms of runtime complexity, it would be safe to say that this approach is 2 to the O of n, 2 to the power of n time, and O to the power of, I'm not quite sure, but it's definitely also space, but there exists probably a lower upper bound than that for the space, right? So this would be 8, 2 to the power of 3 is 8, and we get 6 results. So at least the order of magnitude seems to match. I don't know if it's worth to bring down the space and time complexity more, that the fact that the n are limited to 18 is a strong hint that we have an exponential growth. Otherwise, LeetCode couldn't run our solution. So I think, yeah, I think that's a good analysis. So now let's go to implementing it. And since we're dealing with recursion, let's create a little helper method. And what we will do is we will keep track of how many times we still have to basically do the recursion. And we're also going to pass in a result array. And we're just going to append valid solution to that array as we go along. We could also put this array, this result array here if we wanted to, but I'll put it in here this time. And then we just call the helper. We pass an n and an empty array, and we make the helper return the result at the end. Return result. So that's kind of the scaffolding. Now we need to implement the core. When n is 0, we're done. So we just return the result. We don't have to do anything else. Otherwise, what we need to do is, well, we also need to build up the string, right? So every time we go into the recursion, we have to add 1 digit to our string. So we have to actually keep track of them with another variable. And the digits, we're just going to use a list for that, so that we can just append a new digit to it without creating a new string in constant time. So, and now we have to check, is digits empty? Well, that's the first case. So we could put a 0 or 1 into our string. So if not digits, we have two cases. We would have result.append 0. And let's append it as a string, because we need to return strings. And then we go into the helper. Helper, n-1 digits result. Cool. Now, that means that if n goes to 0, we also have to return a copy. Well, basically, what we have to do is we have to add the final string to the results array. So the way to do that is, and we need to copy it actually this time. Otherwise, you'll see in a second, we're going to, oops, sorry, we have to append that to digits. And after we come back from the recursion, we pop it out from digits. So we're removing the element so that we can continue, with the other case where we append the 1, like so. That's how we do that. Now, in this case here, what we do is result.append digits. Well, we have to turn it into a string, so we can do that with join in Python. Join digits. So that'll create us a string from all of the characters in the digits list. And then we just return that. Cool. So now if we don't have any digits, which means we have the choice of putting 0 or 1 first. But the other case when we can choose between 0 and 1 is if the last digit is a 1, right? Or digits, the last digits is equal to 1. Then we can append a 0 and the 1. Now, if digits is not empty and the last digit is not a 1, the only choice is to append a 1. So we can actually move that down here. So we always execute this case and a 0 only when we're just starting with building digits or when the previous digits was a 1. And that is that should be pretty much it. Yeah. So now it's time to step through the code with the mental debugger. Let's use this example number 2 where n is 1. So we call the helper, n is 1, digits is an empty list, and result as well. N is not 0, but we have n has no digits in it. So the first thing is we append to digits is 0, and then we can call the recursive function, and that decrements n to 0. So inside this recursive call, we run into the first if statement, and we actually just add a string that contains the digit 0 to our result. Then we return from our recursive call, we remove the 0 that we just put in. Next, we place the 1 into the digits array, make a recursive call. N-1 is 0 again. And now we're just adding the 1 as a string to our result. And then we return the result. So we should get back exactly this. And yeah, so I think this already demonstrated the two cases, the two if digits and that. I don't think we have to do anything else. So I'm brave enough now to just hit the run button. Hopefully there are no syntax errors. Okay, all the test cases pass. That is nice. So now let's submit this. And it works. So that's nice. And just out of curiosity, I'm just going to see what other people's solutions look like and what runtime and space complexity analysis they have. It's always good to do that after you've done it. Let me see. Is there anybody who posted a runtime? Well, this could be interesting when somebody uses an iterative approach. That's also good practice, you know. After implementing something recursive, try to implement it in an iterative way. Okay, so there's a dynamic programming solution apparently in of n times m time. Let's have a look at that. That's a more efficient one than the one that we have. Keep generating binary strings from the starting character. If the previous character is 0, the next must be 1. Yeah, we figured that out. Otherwise, we could pick either 1 or 0. M is the number of final binary strings. That's a weird way to put it, because normally you have to know what that number is before you run your algorithm, right? But we know that the final number of binary strings is 2 to the n at most. So yeah, this is not a great analysis, or it's not very well expressed. So what do? So they iterate over the range. So this is just an iterative approach, but it does exactly the same case thing as I do. So this is O of n times O of n squared. But it looks like it's more efficient than my approach. Let's try to understand. So uses a dictionary. And the base case is when the string length is 1, right? Oh, I see. So, oh, I see. So it's building all of the strings from the ground up. So if n is exactly 1, then this loop won't execute, and this is the result. It returns that for n1. Now, if n is 2, it would iterate from 2 to 3. So we will just have one iteration of the loop where I equals 2. It starts with the list of that we had before. And now it iterates over all of the strings inside this list of strings that exist for length 1. Now it checks how the string ends. So the first one ends in a 1. So we're adding to our new result, we're actually adding the two variations, right? The previous string plus 0, the previous string plus 1. And then when we come to this element, it's the first case and we only add the 1. But okay, but this is not more efficient than our solution, or is it? Well, O of n times 2 to the power of n, because the 2 to the power of different possible strings here. So this, I think, yeah, I don't think it's more efficient, is it? And additionally, you are storing all of these lists. So first you're building all valid strings of list, length 1, then you're building all of the valid strings of length 2, length 3, length 4, and you're keeping all of them in memory. So that's horrible. A better approach would be to, it builds this row by row, and the second row contains all valid strings of length 2, etc., etc., etc. So a way to optimize this would be to only have one of these. And we really only need a list. And we just update the list every time. Then that would be basically equivalent to a breadth first search of our recursive approach, right? And so pending these lists, yeah, so this is just crazy space complexity. But why is it n times m time? This is O of n, this is O of n, so this is O of n squared. But why is ours O of 2 to the n? Oh yeah, because this is not O of n, this is O of n 2 to the n. So actually this algorithm O of n times 2 to the n, which is the same as 2 to the n. So actually this one is not more efficient than ours, I would say. Not more efficient. And anybody point that out? Well, no, same questions we have. Yeah, I don't think this one is more efficient than ours. And has worse space complexity. Because we are really only storing the final result, but not all intermediate results for all the other lengths. Since we use the trick with the digit list. And we use depth first search, which allows us to only compute one string at a time. So yeah, anyways, could keep on poking around there forever, but I'm not going to do this. I'll leave that up to you. And happy days, and have a lot of fun implementing maybe the iterative approach.